the tire rod interface essentially behaves in the same manner, right? That was the analogy I gave about us walking. So, this brings us to the question of what are traction limits at a tire rod interface. Of course, it is a different thing to figure out how to determine them. Okay, we are not going to come to that topic in this course, right, but we are only going to learn what happens if we exceed those limits, right. So, what happens if these limits are exceeded? Okay, so those are the two important questions that we would now look at. So, to answer this, we will look at what is called as a friction ellipse. Okay, so this is a very common concept, you know, like used to explain this idea, okay, of this traction limits. Okay, so what is this friction ellipse and what does it give us? Okay, so the friction ellipse is nothing but a plot of the longitudinal and lateral traction available at a particular tire rod interface. So, typically in a plot, you know, we label the horizontal axis as x and vertical as y, right. In this case, we will label it the other way around. So, we will learn label this as x and this as y, right, because we are looking at the tire rod interface from the top. So, this is the longitudinal axis, the vehicle is moving in this direction, and this is the lateral axis. So, x is given for the longitudinal axis, x represents longitudinal axis, y represents the lateral axis, right. So, that is the reason why we mark x and y in this fashion. So, what is this, what does this friction ellipse give us? So, the concept of friction ellipse or this friction ellipse, you know, provides the limits of longitudinal and lateral traction available at a tire rod interface. Okay, so that is the purpose of a friction ellipse, right. Okay. So, if you look at this ellipse, the boundary of the ellipse gives me the limit. Okay, those are what are called as the traction limits. So, that is how much force is there, you know, like that is about it, right. So, in the particular tire rod interface. Now, let us say I am at the origin of this ellipse, okay. Mark O, okay, I am at the origin of the ellipse. That means that what happens, you know, like I am neither asking the powertrain to generate any force, you know, nor asking the brake to generate any force, and you know, like I am not turning the vehicle either, right. Fx is 0, Fy is 0. So, what will happen? This will correspond to what is called as course down, because as we already know, even if I am going on a flat road, we will have rolling resistance and aerodynamic drag acting on the vehicle, right, when we did that powertrain analysis. So, what is going to happen? I am neither commanding my powertrain nor commanding my brake. So, slowly the vehicle will start to slow down and it will stop after some time, okay. That is what is called as a course down maneuver, okay. So, this origin corresponds to what is called as course down, right, if nothing happens, right. Now, if you look at this axis themselves, this positive x axis corresponds to drive and this negative x axis corresponds to braking, right. So, depending on the sign of the force that is developed, right. Okay. So, with that understanding, let us go forward. Suppose let us say I this let us say we assume that this ellipse corresponds to a dry road surface condition, right, and I brake nominally. What happens? Let us say I am commanding this much of braking force, okay. So this is like nominal, like partial braking, right. So I am commanding this much of force, let us say I am going in city traffic, I see a signal, I brake slowly, there is some force which gets applied and I come to stop or I decelerate depending on everything is fine, right. Now let us say I am driving my vehicle and suddenly a child runs in front of me, right. What do? We slam the brake pedal, correct. So the brake system is designed to give us the maximum possible brake force when we completely press it, right. And let us say that point is this and everything is working perfectly, we are at the limit, okay. So this is the maximum braking force that we can get at this particular tire rod interface. So this is the longitudinal traction limit. So now I hope it is clear what is called as a traction limit. So it does not matter which direction we are talking about, the question is traction limit conveys to us what is the maximum force that we can get at a particular tire rod interface, right. So that is the longitudinal traction limit during braking, alright. Of course this is the longitudinal, the top point indicates the longitudinal traction limit during drive. We are looking at braking, so we will look at this. So now we are still on the surface, right, but then we have to be now careful. Suppose let us say a child is running in front of me, right, when I am driving the car straight. So I panic and then press the brake pedal completely, but sometimes we may also try to steer, right. Our natural reaction would be to not only brake but also try to steer so that like we can avoid the child, right. So what happens now, not only am I braking completely, I am also asking for some steering force or force along the lateral direction, not completely, but let us say that is this point, right. So this is like some steering, partial steering, and I am doing complete braking. Now where will the resultant be? The resultant force is going to be here. Is the resultant going to be inside the ellipse or outside the ellipse? This is outside the ellipse, right. So you can immediately see that under this, I am just constructing a scenario where things can go out of control, right. So what is happening is that in this scenario at this particular tire rod interface, does not matter it is the front or the rear, the situation is such that like I have gone outside the ellipse. That means that my tire rod interface will no longer be able to sustain the force that I am demanding, right, both along the longitudinal and lateral direction. Suppose and then like the way we are going to lose some, we are going to pay a price, like we will see what that price is shortly. But then suppose if I want to bring the vehicle under control once again, right, what should I do? I should go within the ellipse, right, or to the boundary of the ellipse at least, right. So you can immediately see that there are multiple ways by which I can go to the boundary of the ellipse, but the two natural choices would be to go from here to here or here to here. Let us say we call this choice 1, choice 2, right. If you look at choice 2, what I am doing? I am going from that point outside the ellipse to the limit of the longitudinal traction. So that means Fy becomes 0. So what does that mean? I can't steer. That is how the vehicle's orientation is not going to change. Although my intention is to change the vehicle's orientation slightly, it may not change, right. What about point 1? Point 1, essentially I am still changing my vehicle's orientation a little bit because I am giving a small steering angle, right. The path of the vehicle will still change because there is still a component of the force along the y direction, but what have I sacrificed? I have essentially ensured that I have reduced my Fx. Now if you want to reduce the Fx, what do we do? I need to reduce the braking force. Now all of us know that braking force depends on the actuation force, right, for a fixed brake factor. Actuation force is brake pressure times area of the actuator. We cannot change the area of the actuator in real time, it is fixed, right, at least in traditional brakes. And so the only thing which we can reduce is the brake pressure, right, and that is what the ABS does, right. It tries to detect this, figure out how much brake pressure reduction should happen and reduces it, so that the brake pressure is lower than what is commanded by the driver. Okay. So the driver commands some brake pressure, because in this experiment I slam the brake, right, I want the maximum operating pressure, but it so happens that I cannot sustain that, right. So it has reduced it. Okay. So that is the task of an anti-lock brake system. But this is only one scenario, there are other scenarios also. I am going to present you one more scenario where this becomes important. Let us say now it rains, same vehicle, same driver, same tire, everything remains the same, but it rains. What is going to happen? The traction capacity or the traction limits are going to decrease. Now what will happen is that this ellipse will now shrink. So let us say I am just drawing this red dashed line showing the shrunk ellipse, right. So this is the shrunk ellipse, friction ellipse, due to a wet surface. Now we have another problem, right. Let us forget steering for the time being. Let us say we are going straight ahead, right, and let us say it is raining. So suddenly I see I have poor visibility, right, and suddenly I see something, some obstacle in front of me. What do? I once again slam the brake. Let us assume that we do not even steer, right. Now when I slam the brake, what am I asking for? I am asking for this, but the new traction limit is this. Then do we have a problem? Obviously we have, right, because I am already outside that ellipse, right, the new ellipse, right, which gets modified, right. So I need to come here. Once again, how do I come here? Reduce the pressure. Okay. So once again, I am slowly getting to how the ABS works, but of course all this is fine for explaining the concept, but in real life do we know these things? Very difficult, right. So I do not know what this ellipse is, right, and this ellipse keeps on changing in real time. How do I know how much it has shrunk? Very difficult to find out. How do I even find out the road condition in real time? See, you and I, the driver or the human being, can look and then perceive that, oh, the road is wet, it is snowy, it is icy and so on. But this has to be automatic, right? How does the tire figure out on its own, right, what surface it is in, right? So the ABS algorithm adds the smartness part to the entire system, right? How does it figure it out? That is a separate, very active field of research. Okay. So but this is this notion of this friction ellipse is used to explain the need for ABS, right. So but then how can that be done? I am going to explain what is called as a mu lambda curve. So for the time being, let us only look at straight line braking. Okay, let us not even look at steering, right. We are only going to look at straight line braking. So let us consider what is called as the mu lambda curve or the traction curve and so on, right. So what is plotted here is that on the y axis we have the friction coefficient mu, on the x axis lambda in terms of percentage, obviously, right. So 1 means 100%, 0 corresponds to 0%. By and large, it has been found out that if you take a typical pneumatic tire which is used in a road vehicle, the maximum friction coefficient or the traction limit or the friction limit varies with slip in this fashion, right. Experiments have shown that this is the typical trend. So, it so turns out that the peak, once again you have to take these numbers in a qualitative sense, right. Even if you take a nice dry concrete road, right, the peak mu comes around like let us say 15 to 20% of slip, right. So, people say in this community like the region, the operating region to the left of the peak curve is what is called as a stable region. The operating region to the right of this is what is called as an unstable region. So, what is stable and what is unstable? To the right of the region, please note that if we reach a point in the right of this vertical red line I drew, so let us say we are somewhere here, what will happen is that like I am already pressing the brake too much, but the wheel is slipping, so the output brake force is going to be low, right, is not it? So, what will the driver think? The driver will think that, oh, my brake is not delivering enough force and may end up pressing even further, and that is going to only make the problem worse, right. So, it is going to push it towards locking, right. One can visualize it from that perspective. But also for a given brake force, if we do not take corrective action, like when the operating state of the tire goes beyond this, goes to the right of this peak point, it will tend to lock very, very fast. Okay. So, this is the point where we have a wheel lock, right, and that is something which we want to avoid, right. Why? Because like we lose stability amongst other things, right. So, we will see what is the consequence. Of course, this is a very simplified notion. As I told you, when you go to advanced courses you will learn more, right. So, this curve first of all depends on lot of things, okay. Even for a particular surface, depending on the normal load on the tire, there will be variations. Depending on the wheel slip angle, there are going to be variations. Depending on the road surface, this curve will change, right. So, figuring out this curve is a challenging process, or figuring out this value of mu is a challenging process. So, if you look at it from a controls perspective, the problem of ABS can be also posed as a problem of regulating lambda, right, is it not? See, if I can regulate lambda, let us say in a region around the peak, let us say between 10 and 20%, okay, then the question becomes like would I get nice stable braking, right. So, this problem of regulating lambda is what is called as wheel slip regulation, okay, which is a very, very important aspect for active vehicle safety systems, right, which essentially work automatically in current generation vehicles, right. Antilock brake systems, electronic stability control systems, all work on regulating the wheel slip, like accurately. But there is a challenge, right. If I want to regulate something, I should know its value at this instant of time. Let us say I tell you, hey, make sure my wheel slip ratio lies around 15%. If I want to essentially ensure that wheel slip ratio lies around 0.15, first I should know what is the wheel slip ratio at this instant of time, is it not? See, that is the whole philosophy of control, right. You calculate the difference between what we desire and what is the actual and take corrective action as and when required. But that is where another challenge comes, because this, if you look at the definition of wheel slip ratio, I do not know what is the current value of lambda. Why? Because I do not know V. So, estimation of wheel slip becomes very, very critical. See, only if I first estimate wheel slip properly, would I know the value or the state at which the vehicle is, then only I can control it, right. That is another problem. I am just introducing you to the issues, right. There is another problem in wheel slip regulation, is that like how do I find out what is the, what we call as the reference wheel slip. In control systems, you know, like we would have heard, what to say, encounter the term reference input, right. That is the desired value, right. Similarly here, what is the reference wheel slip? Okay, this will change based on, you know, the tire road interface conditions amongst others. Okay, dry road, wet road, snowy road, icy road, okay, it is going to change, right. It may be 15% for a dry road, you know, like it can come down to, let us say, 5%, you know, like 4% for a snowy or icy road, right. So, there is a range, right. How do we regulate it, right. So, I have to find out what is the reference wheel slip, okay, and then people talk about mu estimation. There is another challenge because we do not know this wheel slip curve also, right. So, essentially what is the maximum mu that we can get out of the tire road interface, right, or the which is indicative of the maximum traction force at a particular tire road interface, right. So, all these are very interesting problems, okay, which you know, like which are being investigated, right. Of course, we have commercial ABS system, ABS solutions which work on their own proprietary algorithms, right. So, but there are certain components which are standard components of various anti-lock brake systems. We look at those components, we look at how they function, and also we look at what is the impact of, let us say, locking of different wheels, okay, on vehicle stability in the next class. Okay, thank you.